Swayam Prabha. Digital India. Educated India.
So I'm just peeling off one layer of the onion. What is an execution? From a textbook point of view, we are normally told that a process is an instance of a program in execution. So the question really is, what do you mean by instance? What do you mean by execution actually? We saw one view of execution, but what do you really mean by execution? What's happening there? What do you mean by instance? And of course, how do you create a process out of a program, the algorithm? And in the comment, I'm mentioning the PCB, there's something called as a process control block. This is just to, gauge your memory back. So there's something called as a process control block that comes in our way that comes up to us when we look at processes, program to process path. Again, in textbooks, one also says that the purpose of an operating system is to make hardware easy to use, or maybe efficiently manage the hardware, or even present an abstraction to the user. In this part, I'm going to put these as questions. Do we really write an operating system because we want to make hardware easy to use? Do we really write an OS because we want to efficiently manage the hardware or present an abstraction to the user? Along the lines of instance of a program in execution, where we question what do we mean by instance, what do we mean by execution, maybe if we ask questions, what is meant by making hardware easy to use, what is meant by efficiently managing hardware, then perhaps we might get a little bit clarity on the purpose of an OS. I personally always believe that correctness of programs comes first, and once the program is known to be correct, then you can worry about efficiency. So we need to get the ideas of correctness first in our heads. Efficiency is important, I won't deny that. In fact, if you look at the profession where people write operating systems or system software, it's almost nobody ever explicitly talks about correctness. You always seem to hear people talking about efficiency, that we do XYZ thing and then the system becomes more efficient. That is true, but that's because the people who do that are pretty mature experts, and correctness to them is an already done thing. So to put it another way, I mean, you would not want to have a computer system which gives you wrong answers very fast. So let's not, when we are learning, when we are studying things, I think it's useful to have a mindset where we also think about correctness and then we think about efficiency. Having said that, let's come back to the focus of operating systems as executing or running processes. Let's start by reviewing memory management in operating systems. I mean, one could have started with any kind of a management part or whatever, but I just thought maybe to get started, this would be a very useful thing. You would have gone through all of these things in a textbook like say Peterson, Chilbashart's or Tannenbaum or many others that are there. The purpose here is to review those algorithms, but in a slightly different perspective. So what really is memory? I mean, it's some device to remember, and functionality, of course, is to remember. So how do you realize a memory? Realize meaning creates a memory concretely. Well, it needs to use some physical phenomenon that has at least two different physical states, which can be measured, that is, they can be read, and can be changed, that is, they can be written to. As far as the operational part of it is concerned, this is all you need. I mean, that's the kind of a correctness thinking that are there. As far as attributes are concerned, so when you look at actual physical phenomena that are available for you, Um, the attributes would be things like persistence. So do you need power to retain or change the states, or do you not need power? Okay, so magnetic systems, for instance, do not need power. Once you magnetize them, they stay there whether or not you have power or not. So they are said to be persistent. But there are other kinds of memories which require power to maintain their states. The architecture of the memory system. I mean, how many number of units are there? How are they arranged? Are they arranged in one single linear way, or are they arranged in a rectangular way, or whatever? Something of the kind that yesterday we saw Adi describing it. What is the access method? I mean, given that a memory is a collection of memory units, how do you access them? Are they sequential or are they random? And so on and so forth. So the point of attributes is that uh, the central purpose of memory is, of course, to remember, but the ways in which that can be realized give rise to these attributes. All right. The purpose of memory is to remember, and the technology gives rise to different attributes. So let's not really put attributes in front of the purpose. We will see why this is so. Memory is a resource. Let me skip this slide and come to that a little later. So, why is it that we use memory in a computer system? So, just to recall Turing machines, your models of computation that are there, the Turing machine models computation in terms of a head that actually has the capability to manipulate symbols, and a tape which holds the symbols, which supplies symbols to the head and stores the symbols that the head tells it to store. So the tape really is the memory, and in computing machines, the CPU is the one that realizes the Turing machine head, and the primary memory is the one that realizes the tape. Note the phrase primary memory. Primary memory is primary because the CPU uses it for instructions and data. It has nothing to do with attributes. Which means that if you arrange your say electronics appropriately, then you could have your hard disk as your primary memory, the magnetic disk as a primary memory. As long as the CPU uses it for its instructions and data, that is what will make it primary memory, and not the attributes, whether it is persistent memory or whether it is a sequential or random access. That does not matter. And any memory that is not used by CPU is for instructions and data is really secondary memory. Now, this means that if we have something stored on secondary memory, in order to use it, we must get it onto primary memory. Only then the CPU can work with it. That's, of course, is something that we know. We call it as loading. Anyway, so here's a representation, a kind of a sketch of the memory. I'm just showing it as a linear array of n locations labeled 0 to n minus 1. Addressed as 0 to n minus 1 and labeled as m0, m1, m2, etc. And I'm just writing that as a set, capital M, which is made up of n memory units, m0, m1, etc. to n minus 1. What is the size of a memory unit, a particular MI? Well, we'll assume a typical size, say 1 byte. In other words, this is a memory of n bytes. Okay. Also, any k-dimensional memory, this is one-dimensional, it's in one line, it's one-dimensional memory. Any k-dimensional memory can be represented in terms of as a one-dimensional memory, that is an array. Just to be a bit clear, we will assume that the memory is read and write, that is, it is reusable. So every memory unit, because it can be written to, it can be reused. How do we represent processes? Again, it's a set of P of processes. P0, S0 is the amount of memory that P0 requires. P1 requires S1 amount of memory, and so on and so forth. So it's a finite set of K processes. Um, and our focus is, of course, just the memory, the bytes. So let's start with a simple problem. I mean, we want to allocate a single process. This means that the set P has only one member, P0, process P0 requiring S0, and a set of n memory locations. And our problem is to allocate memory for P0. Okay, let's solve a simple problem and then we look at how to worry about the others. So here is a few questions. I mean, how do we know if allocation is indeed possible? How do we know which memory unit is in use? You might want to spend some time thinking about how will you allocate memory for one process. Let's take a few minutes, 2 minutes or something like that, to uh, work out, in our notebooks or whatever, how will we allocate memory for one process. We know that the amount of memory, we have n units of memory, and we know that P0 requires S0 amount of memory. Hopefully you have tried something and there is some kind of algorithm that you have sketched out, which will allocate memory for one process. Uh, the way I'm going to do is, first I'm going to define a memory region that is a subset of memory starting at some k up to some k plus n, and that memory region is going to be labeled as R. I've written up a pretty, I hope, a possibly intimidating predicate, but it essentially describes what part of the memory is in this region. So for all I, which are natural numbers, I limited to 0 to n minus 1. If I is less than k and if I is greater than or equal to k and I is less than or equal to k plus n, that mi is the one that is a part of this region. That's what the predicate describes. But let's go ahead. I am going to use two sets. One set O is a set of occupied regions or allocated regions of memory, and another set F, which is a set of free regions. At the start, O is going to be an empty set and F is going to be all of memory, that is the set M. I'm going to say that the start address is -1 because it's not a valid memory address. Memory addresses range from 0 to n minus 1. And to begin with, the length of the region is 0. Pictorially, I've shown P0 with S0 units and M with N units. They visually look same. But please note, it is S0 and N. Okay. My intent of doing it like this was to get you clear that you need to focus on S0 and N. Whatever way the visually it looks, that is irrelevant. So anyway, here is a sketch of that algorithm. There is a single processor allocator which takes in a set M of memory, the amount of memory required S0, and a set of occupied regions, and returns an updated set of occupied regions and an updated set of free regions. Okay. So it starts by saying that required is S0 if required is less than or equal to available, which means that if there is sufficient memory, only then proceed with the rest of them. For each location mi, if mi is a member of some occupied set, if that is false, only then that corresponding I is a start address, and then increment the region length. The moment the region length becomes the same as required, you have a new region which starts from start address to region length. That's what you get as a new region. Update the occupied region, subtract the region from the free set. Okay. There are else blocks which I have left empty. Okay. But you get the idea. It is possible that this particular algorithm, that the way I have put in, has some errors, one or more errors. I don't know. I invite you to look at it and check if it is right or wrong, and if whatever are the errors, remove that and make this algorithm as error-free as possible. Okay. The key point, however, that I want to stress over here is things like check whether you have enough amount of memory to allocate in the first place. That is done by the predicate required is less than available. As we create more or better memory management algorithms, I won't say better, I would say different memory management algorithms, the way this gets expressed, whether you have enough memory, that details will change. But the idea that you need to find out whether you have enough amount of memory, that question still remains. That will remain everywhere. Which is why I sort of put up this algorithm in this way. All right. Having done that, having allocated memory for a single process, here are some questions and for your insights to cultivate some insights. How do you compute whether a element memory is a member of some occupied set or not? What are the data structures that are shown on the screen? Does allocation necessarily start at M0? You might want, these are questions for you to think about, answer for yourself, discuss. In the meanwhile, let's look at allocation for many processes. Well, that is fairly simple. A many process allocator will take the memory, the set of memory locations, the set of processes P, the set of occupied regions O, the set of free regions F, and return an updated set of occupied and regions and free regions. The idea of a many process allocator is fairly simple. All it does is it repeats the single processor allocator for each process in the set. For each PI in P, the required is just the SI, the number of bytes for that particular process. And available is the length F. And now you run the single process allocator. Okay. There are, of course, limitations with this algorithm. There are some problems with this algorithm, etc., that are there. And this is something that we have already studied in the textbooks. However, the point of this is that, come to think of it, this is just the first come, first serve algorithm. At the end of the day, this is just the first come, first serve algorithm. Okay. What did we do? We just did a allocator for one process, and we did an allocator for many processes by simply repeating the allocator for one process. There were many assumptions hidden in our approach. So here are some implicit assumptions now. So the set P of processes is taken as is. So when I ran the many process allocator, I took the set of processes as is and just went through the processes as they are. Similarly, I just took the set M as is. I mean, I did not do anything with the set M, that is the memory locations, the set of memories. There was an implicit assumption that elements of P are taken as a whole or not at all. So either a process gets allocated as much memory as it requires, or it never gets allocated. I've also assumed that the set P is completely specified at start. That is, before the algorithms for allocation ran, the set P was given to us. Finally, the last one is slightly subtle. The set M is exactly our mental model of the real physical memory. In other words, in our mind, when we imagine the set M0, M1, M2, etc., we can establish a direct relationship of M0 to an actual physical location in the physical memory, M1 to an actual physical location in the physical memory. We are assuming that what we are thinking is exactly what we are seeing on the machine. In that sense, M is an exact mental model of real physical memory. Now, we had sort of assumed that, or maybe we never even realized that, but let's see what it helps us with. So, let's take the implicit assumptions one by one. The set P can be rearranged. That is, the set of processes, instead of taking them as is, the set P can be rearranged. I can sort of rearrange the set, the processes that are there in the set and do something before I actually run the single process, before I actually run the allocator. Instead of taking the set of memory as is, I can first organize the memory in some way before I perform allocations. Similarly, I don't have to take take a either or none approach for each element, for each process. I can think of taking a process, cutting it into pieces, and allocating memory in pieces. Why should I allocate the memory for an entire process or no process at all? Okay. Why do I need the set P to be completely specified? I might, it is possible for me to also add processes to the set as time progresses. Okay. Something that occurs in interactive systems. By the way, with the set P is completely specified at start is something that occurs in batch systems, by the way. But let's look at it a little later. If the memory set that I have does not directly correspond to the physical memory, then I can use it to model what is called as virtual memory. We will see this in a short while, but I hope you get an idea of what it means by the various assumptions that have gone in and how those looking at those assumptions and playing with them starts giving you different memory management algorithms. So let's have a quick look at them. If P can be rearranged, then one way to do that is to sort the processes. Sorting will require some number to be given to each process. The question then is, where do we get that number from? One obvious source is the internal information in the process. For example, its own requirement, its own size. That itself is a number. So if you sort according to the size, then you get either shortest job size first or shortest job size last algorithms. But then the numbers can also be given externally. I mean, instead of looking at some property of the process, we might look at numbers being given externally. They are called as priorities. You might say that you want to execute process PI first and process PJ next by whatever reasons for whatever reasons you wish. In other words, PI should have a higher priority, in which case that should come first. Organizing M. One way is to do is what is called as fixed size partitioning. So in the entire set M is divided into chunks of memory. Instead of 1 byte, you say k bytes is one chunk, and the entire set of memory is divided into chunks of k size each. So there will be n by k number of chunks. Another variant of that is the buddy allocation. If I allow myself to divide the processes, they basically not load the entire process, then it allows me to do segmentation or paging. Adding processes as time progresses, that's exactly what I said, batch versus interactive. M can model virtual memory. So the set that I use, it need not correspond to the physical memory. In fact, it might be it is just there in my mind. So it is it's a virtual memory in my mind, and then I later on use different techniques to associate it with physical memory. The techniques I use to associate with physical memory would be swapping, segmentation, and paging. All right. Here is an example of paging. The set M dash is the virtual memory. That's the set over which I'm going to perform my allocations. The process is P0 with size S0. And I'm going to cut that and allocate that onto the memory M dash. And then in a separately, I'm going to associate memory M dash with the real physical memory M. And that is done by M0 to some region in M, M1 dash to another region in M, M2 dash to another region in M. And these associations will be collected in a table that will be called as a page table. A data structure will be called as a page table. Note that as dividing the allocation in two layers allows us to implement the latter part in the system, which is hardware controlled. And then as far as the programmer is concerned, the process is always there in virtual memory and not in the physical memory M. All right.
Excuse me, sir.
Yes.
Sir, like if we have a process and we divide it into a particular fixed segments, so are these allocating in a contiguous way, like first and then do the second, and then if you don't find the third, then don't allocate it?
Segments or pages?
So we have processes which are divided into particular fixed segments, right?
Fixed size pages. They are actually called as pages. The fixed size
Okay,
divisions
fixed page.
are called as pages. Yeah.
Okay, so we have divided into fixed sizes. So by allocating it, so we are allocating memory to it. So process
Yes.
0 will be allocated to M0, then process 1 will be allocated to M1 dash only, like in a contiguous way only.
No. So it's process. It's not process one, by the way. It's process P0 divided into pages. Page number 0,
Yes,
page
sir.
number 1, page number 2. The entire thing is just process P0.
Yes,
Process
sir.
P0 has been cut.
That
Yeah.
page one. Yes, sir.
Yeah. So
That page
page.
one will be. Yes, sir.
Yeah. Go ahead. Page 1 will be.
Yes, sir. Yes, sir. So that page one will be allocated to the M1 dash, like in the continuous manner with the M0 dash, or it can be allocated anywhere in the memory.
You can actually allocate it anywhere, but that's a virtual memory. You can allocate it anywhere, but it's because it's not really physical memory. It makes sense to just put it contiguously. That's all.
So, so what is the like if we are putting it the contiguous way? So why did we divided it in the first?
Oh, that's because we don't have to load the entire process in the actual physical memory. What we really do is the actual magic comes in the later part where M dash is associated with M, that is the page table.
Yes,
Okay.
sir.
In M, you don't have to allocate all M0 dash, M1 dash, M2 dash. Not all of them need to be allocated. You can just as the arrow shows somewhere in M. All right. Now that is the physical memory. That is what is going to be used by the CPU for instructions and data. So the CPU will execute the code in whatever is wherever M0 dash is allocated. And when that part is finished, you can allocate M1 dash next. So
Yes, sir.
the entire process P0 can be allocated into the memory M piecewise. You don't have to allocate it at all. I mean, all of them need not be allocated in one shot. You can do it piecewise.
Okay, and if something like if we have divided it into this M1, M0 dash, M1 dash, and so on. Now, when we are putting it to our memory, so if suppose the that page does not find a memory, doesn't find a available memory, so what
Mhm.
will happen?
Uh, What will happen? Well, you will make it happen. When you write an OS, you are going to write an algorithm which will say, okay, I did not have. Sorry.
Yes, sir. Yes, sir.
Okay. When what?
There is some crosstalk. Can we?
Oh, okay. There is a crosstalk. Okay. Okay. So what I was going to say was, you write that what is to be done if you cannot allocate physical memory to a frame M dash. Normally, what
Yes,
you
sir.
do is, uh, normally the operating system will always try to allocate some physical memory for a given frame in M dash. In order to do that, it will look at other frames that were already allocated and try to see which of them can be discarded. Okay. You have various algorithms like least recently used page or things like that that can be used to decide what other part of the physical memory can be freed up. Okay. That program will try to make space to allocate a particular M dash, whatever is there. Okay. Does it make sense?
Okay. Yes, but still I have a confusion. Like if we have this process divided into pages,
Mm-hmm.
0, 1, 2, 3. Suppose it finds location for 0, 1 and 2, but
Right.
it doesn't find the available for 3. So will
Right.
that process will be allocated? Like the third part is not being allocated to the memory.
Right.
So that process will be like not fully loaded into the memory. So will it continue to work cycle by cycle, or
Yes,
will
it
it
can
wait for the
continue.
memory to be free and let the third page of that process also load, and then I will continue?
So the process can run for whatever is there in page one, page zero, page one, and page two, right?
Yes.
And when the process comes to a point where it runs page three, because there is no memory for it, the system will page fault.
Yes, sir.
And
So
you as an operating system writer will write a page fault handler. What will the page fault code do? It will now look at other pages in M, free them up, and load the third page of process P0 into that freed up region in physical memory. And then the process can continue.
okay, sir.
So
Yes, sir.
as far as the process is concerned, it just experiences a slight delay.
Yes, sir. So, but other one will, like, if memory that M dash is full, so our page handler will see, okay, which one I can free up, and then it will free up like with any policy, like LRU policy and
That's right.
anything.
That's right. That's right.
Oh,
Okay.
okay, sir.
But the advantage
Thank
here
you.
is that because it is piecewise, you can in principle load a process which is larger than the physical memory M.
Yes, sir. Like allocating half of it in the first part, then by replacement policy, we can just remove all those and load the second half.
That's right.
Okay,
That's
sir.
right. Okay.
Yes.
So here, when I think of paging, I'm actually combining two assumptions that we had talked earlier. One was being able to divide the program into pieces, and second, the set M need not represent physical memory; it could represent virtual memory also. And then I take a separate step to connect virtual memory to physical memory. All right. Together, that is
Yes.
what is called paging in a textbook. Does this make sense?
Yes, sir. Yes, I got it.
Okay.
Thank you, sir.
All right. Are we good so far? I have spent a fair amount of time on this idea, because now the next part is to look at secondary memory and CPU scheduling. That's going to be very simple now. If this part is all right, then looking at secondary memory management is actually trivial. Well, as far as secondary memory is concerned, it's again a system of n memory units, but this time one memory unit has a different size. It's one sector or one cluster or so on and so forth. But otherwise, it's just the same thing. Again, three-dimensional memory can be represented as one-dimensional one. So for example, a hard disk with cylinder head sector, that is three-dimensional geometry, can be represented as 1D. Now, instead of processes, as far as secondary memory is concerned, we have files. So instead of set P, we have set F, again the same way. We should think of FI as the name of the file. We'll come to this in a short while. But note that now the memory allocation problem is the same for primary and secondary memory. You just need, whether it is a process or files, you just need to store a set of bytes in the memory. Okay. The unit of allocation may differ. In primary memory, it's 1 byte. In secondary memory, it's 512 bytes. So our single file allocator is now going to have a slight change. I mean, it's going to think of something called as the allocation unit size. I've put up as 512. You can put it up as whatever the size your device says. And now the required memory is the number of bytes divided by allocation units. So you're really looking at the number of allocation units on the secondary memory that you need. That change is one that should percolate through the entire algorithm. In one particular case, I have shown if required is less than or equal to available by allocation unit size, that is a change. You might want to see what are the other changes required in this algorithm for file allocator. The moment we solve the problem for allocating one file, we can do for many files also. But again, there are the same sets of assumptions over here. We assume that the set of files is taken as is, the memory is taken as is, and so on and so forth, except the last one. In primary memory, our set M was an exact mental model of the real physical memory. In secondary memory, this assumption will be real. M will always correspond to real memory. Okay. But otherwise, the things can be same. So you could rearrange the set F by sorting or priorities or whatever you want. You could pre-organize the secondary memory. In fact, that is what is done. Pre-organizing the secondary memory is called formatting the memory or creating a file system on the memory. You could cut elements of the file and store it piecewise. That's how actually it's stored in normal operation. All right. Here is the same picture of file on a physical memory, secondary memory M. The first part of the file, oh god, the labeling is changed. I forgot. Instead of P0, please read it as F0. This is called as a file allocation table. Let's look at that a little bit more. We now come to what is called as a file system problem. What we have understood is the allocation algorithms are same for primary and secondary memory. You can think of the allocation algorithms as being parameterized by things like allocation unit. So a single file, a single allocator is parameterized by allocation unit of the memory system. If it's 1 byte, it's for primary memory. If it's 1 sector, it's for secondary memory, and so on and so forth. But the file is still just a set of bytes. We do not have a way of distinguishing one set of bytes from another. If we are storing multiple files, we don't have a way of distinguishing them. if we are just looking at them as a set of bytes. How do we do that? The solution is to uniquely name each file. How do you name a file? Well, you just associate a string with a set of bytes. That string will be called as a name. And then you create a table. On one column is the name, in the other column is the set of bytes for that name. In fact, not the set of bytes, where those set of bytes are on the secondary memory. That is what is the core thing that you need to do. Now, given that you need to create this table or of this information, you can think of data structures that you can use to realize this. All right. The other part is interesting. How to make the name unique. So, for example, can you split the entire name in parts, and can you organize the parts in some data structure? Oh, yes, you can. We normally organize the full name into a data structure called as a tree, and the parts of the data structure are directories or folders and the final file name. So the entire name of the file starts from, if you're on say a Windows-like system, then the drive letter followed by the first folder, followed by the second folder, and so on and so forth until you come to the name of the file. This entire thing is the unique name of each file. We call that as a path name. Here is the logical view of the FAT file system, that table that is there. The file name here is made up of two parts, name and extension. There is some tyui.jpg, and the start cluster pointer to the first thing is head, is given in the third column, and there are other columns with other information like date, time, etc., etc. You also have F0, S0 as an illustration over here, and here is the picture. On a physical disk, you have a boot sector. There are two FAT areas and the root directory area and the data area, of course. The root directory was a table that we just saw. The name was tyui.jpg. The start cluster was 2, which is the pointing. It points to that FAT that is shown. So at 2, when you go to the when you actually go to the file allocation table, you will see that at 2 you have an entry 3, which means that the next part of the file is in location 3. Okay. At 3 you look at the next location, that is 4. That is data area number 4. And at 4 you have a marker of end of chain. That is, there are no more sectors on the disk where the file is stored. This essentially is the FAT file system. What have you done as a result of file system? You are now able to identify a bunch of bytes by names. Human beings can understand names, not a bunch of bytes. Okay? The entire purpose of a file system is to create this logical view of information. Information instead of just a set of bytes, a file system allows you to view them using names. That is why you do all this mess of file systems. All right. Let's now look at CPU time management in operating systems. Okay. Oh, again, what is a CPU? It's a device to execute and functionalities to execute. Realization, well, I mean, that is a harder problem. It requires a lot of details over here. So I've just put them as a winky smiley. But it executes instructions that execution is sequenced using a clock. And the source of instructions is, of course, your program. This means that running your program requires some number of clock ticks on the CPU. It consumes some amount of clock ticks, and that is what we call as CPU time. Okay. The CPU time allocation problem is, we want to set up the computer system so that CPU is given to the instructions from our program. Okay. This makes CPU time as a resource just like memory. But unlike memory, CPU time is not reusable. Once a time instant occurs, it is used, the time instant is gone. It does not come back. Therefore, CPU time allocation can only be done in future. Hence, we call it as scheduling. All right. Here is the representation of CPU times. You have a set T, T0, T1, and so on and so forth. But know that this set T is countably infinite. I mean, you cannot know what is the last moment of that time. Okay, it's countably infinite set of time units. To reiterate, the time instants are in the future, they cannot be reused, and the set T is infinite. This distinguishes CPU time as a resource from memory as a resource. Memory is finite, it can be reused. Okay. All right. We again represent process using the usual picture. P0, T0, but this time T0 is the amount of time that the process P0 requires. Note that, I mean, the time T0 that a process takes actually can not be calculated or computed algorithmically. If you want, I mean, that if you being able to have an algorithm that finds out how much time a process takes amounts to solving the halting problem. That cannot be done. So actually, writing P this way in some sense is not very honest, but the idea here is conceptual. That I'm going to imagine that there is some time T0 that is required. And I'm going to think of my allocation algorithms using this, and then work with the idea that actually I don't know T0, so what do I do? All right. Again, the single process allocation straight away is simple. The questions change a little bit. All right. So for example, how do we know which time instance to use? That becomes an irrelevant question because we are always going to use a time instance in the future. All right. Again, the same way, single process allocation, there are two sets, set of occupied intervals and set of free intervals. You might want to think, what are these sets normally called in textbooks? Here is the single process scheduler. It is very similar in structure to what we have already seen, but there are some variations. You can have a look at this. These slides will be shared anyway. Again, same sets of questions, but this time for CPU time. Again, a mini process scheduler. This is again a first come first serve scheduler. Again, an introspection of the same kind. And again, the hidden assumptions. Notice that this time we do not have the virtual memory kind of an assumption right now. Here are the possibilities. The set of processes can be rearranged according to size, according to the time they take. This gives us things like shortest job first scheduler. Okay. You could pre-organize the time in future. This is something that is required when you have real-time constraints. When you want a response within a certain amount of time, you are going to have the well-defined times of response, which means you pre-organize it. You cut elements of P into pieces, but this time the pieces are of time. So the execution time of the process is cut into pieces or intervals. The round robin is an example of that approach. Notice that round robin has similarities with paging as far as the ideas are concerned. The implementation wise, of course, because the resources are different, the algorithms look very different. But conceptually, they are pretty similar. All right. That was a whirlwind tour of the various algorithms that you have done as far as managing resources is concerned in an operating system. Let's begin with dealing with interacting processes. But in order to do that, we need to worry about the central concept of an OS process. We need to sort of understand what that process is.